Okay.
with ice on it.
Hands are going. Bubbles.
Oh, that's cold.
Hands go, hands go, hands go. Bubbles go faster when your hands are on it.
Now the idea is you have two students sitting across the table from each other.
Yeah.
And they take turns. When the bubbles slow down,
The other person puts their hands on it. I've seen you do this lab a couple times.
so at any rate, so we'll go through this real quickly. And the idea is we talk about what a model is. And a model is an explanation. And what we want to do is, why are bubbles coming out? Some kids will think, well, it must be boiling. And no, it's not boiling. So rather than go through the whole thing.
Mm-hmm. And then when you put the thing of ice on top.
Yeah.
I'm like.
I know. Or we could do.
Oh, heat it up. Cheat.
Cheat.
What is this? And there we have it.
Okay, now, water's not boiling. That this is not working. I mean, this is working, but that's not working.
Yeah.
All right, so you do this for a while, and then we keep the ice on the top.
See. With one.
Okay. So did water go up?
Uh-huh. And water spilling over on the inside.
All right. So that's enough of that.
Okay.
Okay. The important thing is there ain't no such thing as cold.
Mm-hmm.
There's heat. And you know the kinetic molecular theory, all matter is made up of particles in constant motion. And you just saw the video, the Eureka video.
Yeah, I watched it.
And here's the deal. Particles that are in motion, anything that's in motion that has mass, has kinetic energy. So this is a model of a molecule. They're in constant motion.
Mm-hmm.
And if there's more motion, they have more kinetic energy. So as they vibrate, they have more kinetic energy. And the faster they vibrate, the more kinetic energy they have. And here's what we just did. And Air is composed of particles. In terms of particles, what happened in the flask to make the bubbles come out? That's the challenge. Okay. Well, what did happen inside the flask?
The flask was cold. Put our hands in the flask, and bubbles came out, which means that air from here is being pushed out.
Okay, by what?
By how fast the particles are moving.
Okay. Well, as the particles move around, you saw the video about the wasps in the
Yeah.
balloon.
Mm-hmm.
As they move faster, they exert a greater pressure.
Mm-hmm.
Okay.
Oh, there you go. It has to do with pressure. That's right. Okay.
So they increase the pressure. And why are they doing that? It's because their volume increases. So you have heat goes in, volume goes up, and pressure goes up.
Mm-hmm.
Okay, and then so then we put the ice on there.
Mm-hmm.
And now, heat out, volume goes down, pressure goes down.
Mm-hmm.
Okay, and as the pressure went down, it pulled water up through, it took up less space. What happened is the air inside, some of it left.
Yeah. Yes. Yeah. It's like kind
And-
of like with the almost with the goal of getting to a vacuum, but not really. It's not gonna be a
Right,
vacuum,
and
but-
so what happens is every bubble that goes out, there's that much less air on the inside, but that's fine because the particles are moving fast, they've expanded, they take up more space, and they're fine. But when we put the ice on here, the particles cool down, they slow down, they take up much less space, they have less volume, and so that less volume creates lower pressure, which pulls the water in.
Yeah.
Okay, so now I would have them sketch a graph, but I've got one right here. Okay, and so what happened here is we put our hands on there. Let's say it was right about here.
Mm-hmm.
Well, no, it came out of the ice. So inside we can assume that it's 0 degrees Celsius. As we put our hands on it, the volume increased. There's only so much space on the inside, and so some of the air had to go out. Then we put the ice on it, the volume decreased. Again, I didn't get back to 0.
Yeah.
And you're familiar with this thing, this extrapolation, the relationship between temperature and volume. And the idea is as the temperature continues to go down, the volume becomes less and less, and then we extrapolate that back to absolute 0.
Sweet.
This is not working at all. No. Okay. Multitasking.
Sweet.
Okay, here's the big idea. Thermal energy is the total energy of all the particles in an object. Thermal energy is symbolized by the letter U. Sometimes it's called the internal energy. And it's the total energy of all the, both the kinetic and the potential, because there are potential as well. As the particles are moving around, you have your ideal bond length. And when they're closer together, that's a chemical potential. That's a potential energy. When they're farther apart, there's less potential energy. So you have the energy of motion. You also have the energy due to the bonds stretching and compressing. That's the thermal energy. It's the total energy. And you probably know this anyway. Okay, the big idea for kids is changing the energy of the particles makes them slow down or speed up. It's a simple thing, but it's important. And when that happens, there are two things that can happen: a change in volume or a change in state. And this reminds me that I have an overhead. I'm not going to get the projector out, I'll just show you. That's not it. That's not it. What is this? Oh yeah, this is it. All right, so thermal energy. Where is it? Here's the thing where I've got a tub on one side that's got hot water, hottest out of the tap, and then ice water on the other side. You put your hands in both, count to 5, 1, 2, 3. They start getting acclimated to the temperature, and then you put them into room temperature at the water. Room temperature water in the middle. The one that's in the hot water feels cold. The one in the cold water feels hot. And so that's, here we go. All right. So solid, liquid, and gas, the difference between these three states is their energy. Solid is low energy, gas is high energy. As you put energy in, a solid melts. You continue to put energy in and it boils or evaporates. Okay, and so what is required to go from a solid to a liquid? Energy in. What's required to go from a liquid to a gas? Energy has to go in. And the converse is true. You have a glass of iced tea on a humid day, and you get the water on the outside, you get the condensation on it. That's because the low temperature glass is pulling energy out of the water molecules, causing them to get dense. Like, wasn't that one of the videos I had you on?
I didn't get to watch the third one.
Yeah, you're all right. Okay, turns it into a liquid. Well, then how do you go from a liquid to a solid? What's going on in the freezer when you put the ice cubes that are liquid in there? You have to take energy out in order to go from a liquid to a solid. So this is a very important
Heat of
step
vaporization, yes.
in the stuff about the heat. We'll get to in a minute.
Yeah.
And since this is not working, we're going to turn it off. Oh no, let's keep it.
Is
going.
it doing?
Yeah. See, what you had is that should be a flat plateau. When there's ice in there, the temperature doesn't go up.
Oh, I see. Cool.
We'll get to that.
Cool.
All right, then you watch the video. And so our first big idea is thermal energy. That's the total energy of all the particles in an object. And heat is the transfer of thermal energy between two objects because of a difference in temperature. Which was at a higher temperature? When I first brought this out of the ice, my hands were at a higher temperature than the glass, yes?
Yeah.
So my hands felt cold. Why was that?
Because
If there's no such thing as cold, why is it? I know!
I don't know. I don't explain it.
Well, heat is transferred between two objects because of a difference in temperature.
So it's the
There's a
difference in
difference in temperature between my hands, higher temperature, the glass, lower temperature. Heat flowed out of my hands into the glass. Now that feeling, that sensation, ever since we were first born, we've been told is cold. There's no such thing as cold.
That's what Justin remembers that.
There's no such thing as cold. There's heat. Well, that's good. I'm glad that he remembers that. Heat always travels in the same direction. Some people say, oh, heat rises. Not all the time. If you take a hot pan off the stove and touch the bottom, heat is going down.
Yeah.
So it always goes from high temperature to low temperature. So heat flowed out of my hand into the flask. Okay, and then the flask warmed up. The flask was then at a higher temperature than the air. Heat flowed out of the glass into the air, and that caused the temperature of the air to go up. All right? So we got two big ideas here. Thermal energy is the total energy of all the particles. Heat is thermal energy going from one place to another. And there's no such thing as cold. There's heat. Oh, well, we'll get to this in a minute. This is one of my favorite things here. Isopropyl alcohol. Hold out your hand. Feel that?
Yeah, it feels cold.
Okay, this is the same temperature as the room. This has been in the room for 20 years. All right. So why does it feel cold?
It feels cold because of the difference in the thermal energies. The difference in the heat. I'm sorry.
Well, which is at a higher temperature, your hand or the alcohol?
Oh, my hand.
Okay. And so, what direction is heat flowing?
From my hand to the alcohol.
And what's happening to the alcohol?
Oh, the alcohol is having it. It's not heating. Is it heating up or it has a higher
Well, the
thermal
temperature is
energy?
going up.
Yeah.
The temperature is going up, and if I blow on it, notice how cold it feels?
Yeah.
Okay. Now, is there as much alcohol in your hand as there used to be?
No, it's definitely.
Where's it going?
It's evaporating.
What does that mean?
It means it's getting enough thermal energy to break free from what the liquid that it's
Evaporation
with.
is what happens between liquid and a gas.
Yeah,
Yes?
yeah.
Okay, so it was a liquid and it's disappearing into the air. And what does it take to go from a liquid to a gas?
Energy.
Energy in. Where's it coming from?
My hand.
So you can see the connection between that
Yeah.
overhead back there and
Yeah.
this. There's no such thing as
So-
cold, it's heat.
So you feel cold because of the energy transfer.
Because you're not dressed properly.
Yeah.
So, you got bare legs.
Yeah.
You go outside right now, it's about 53, 54 degrees Fahrenheit, and heat will flow out of your skin into the air. Okay, and you will feel cold. Okay, well, what happens if you put some sweats on and you go outside?
You won't
Now
feel
there's
cold.
a barrier between your skin and the air on the outside. Now heat transfer, it's like when you get into bed at night and the covers are cold. Ooh, boo, the covers are cold. But then after there for a while, they warm up. Why do they warm up?
Because your body heat is transferring.
Heat is flowing out of you into the heat. So that heats
worst.
up and you're heating up the entire stack of covers on top of you. Well, the air temperature, I assume, in the room is lower than your body temperature, so heat leaks out into the room. Okay, well, what happens if you get too hot in the night?
Take the covers off.
Yeah, you kick your leg out.
Yeah.
Kick your leg out, and what happens is now heat is flowing out of your leg,
Yeah.
lowering your body temperature. This is working. Okay, notice that we've got
Cool.
bubbles in here now, and it's starting to level off. Okay, so having kids think about there's no such thing as cold, there's heat, is a life-changing thing. But it is, and what we're doing is we're asking kids to change their way of looking at the universe. Right. What is a thermometer?
What is a thermometer?
At this point, I would hand out thermometers. I'd say, here's Mr. Thermometer. He's long, he's thin, he's made of glass. If you break him, I'll throw you out of class. So, what is a thermometer? Physically, what kind of a thing is it?
Glass, and then do they still have mercury inside?
Not anymore, no.
Yeah. So some sort of
It's an alcohol.
okay, so some sort of liquid that expands, that changes.
A thermometer is a long, thin tube
Oops.
with a liquid-filled reservoir
And a ruler on the side.
and a ruler on the side. That's what that is. That's a ruler. Okay, and you got the reservoir down inside. You can't see it because it's in the armor.
Oh, I see it there.
Okay,
Bada boom.
so what does the thermometer measure? It's got a ruler on the side.
Same.
And the kids will say, temperature, it measures temperature. It measures heat. I know this, I've heard it 1,000 times. So what is it actually measuring? It's a ruler.
Yeah.
It measures changes in volume. Okay, it measures a change in volume. That was at 20 degrees. Hold that in your hot little hand there. And because that's what the students do. And it was down at 20 before. What is it now?
23. It's rising a little bit there.
So what happens is you have your hand in the reservoir there, and what's happening is heat is transferring from your hand into the thermometer, into the glass, into the metal, into the glass.
25.
and then into the liquid. And what happens in the liquid?
And so it's
Particles move faster. They take up more space. They expand. So
Uh-huh.
what causes the volume to change?
The heat transfer.
coming in, the particles, which is thermal energy, is transferred to the particles. They move faster and faster. They take up more space. They go up the tube. Okay, and this is one of those things that's also an important thing, because what's a thermometer? What's a thermometer?
Yeah.
They take things for granted. Okay, the volume of the liquid is proportional to kinetic energy of the particle.
Uh-huh.
Simple thing. Okay, now here is it's the holy trinity, the thermal trinity. You've got thermal energy, you have heat, and you have temperature. And there are differences, in science you have to have specific terms, and when you use a term, it has to have a precise meaning. You've got to know what you're talking about. If you don't use the terms appropriately, you sound ignorant, which you may or may not be. Hang on a second. This will be very important later on.
Okay.
Okay, so temperature is the average energy of all the particles that make up an object. And what I do is at this point, I put 2 meter sticks on the wall. You've seen the 2 meter sticks over here. And I have the tallest kid in the class come over with a ruler, and I have a short person who has good handwriting around the board, and we take the height of do you know how tall you are in centimeters? And so we find the height of everybody in centimeters, and we write it on the board. You got 40 kids in the class, you got 40. Say, okay, boys and girls, and I have her put them in columns of 4 or 5. And okay, this table add up this column, this table add up that column, until you've got every table's got a column, they add it up. You put the total, you add what it is, what's the total, then okay, now add up, what's the total height of the class? And we usually come up with something around 60 meters.
Yeah.
Okay, and 60 meters is how tall the class is. Okay, all right, and I'll do that for every class. And okay, what's the average height of the class? And the average height of the class is usually around here.
You just divide it by, our 40 kids.
We count out how many students, and once again, what's an average?
Yeah.
They're high school students, they forget. So, and so which one of these is like temperature? The average height. Which one of these like thermal energy? The total height. Okay, so I've got all the...
That's really helpful.
I've got all the data over here, total height, average height, and some classes are huge. I have the basketball team on there, and 6th period is usually the heavy Asian period. Where you got the Laotian kids. And what'll happen is that you'll have a big class with a smaller average height than a smaller class and a larger average height. Well, why is that? How come? What if we had a class full of 6th graders? What would be different? Okay, all right, when I say, what if you had 6th graders? And they say, well, the average height would be less. Would the total height be less? Yeah. So I didn't say how many 6th graders you got.
Yeah.
What if you got 1,000 of them? Then,
yeah.
And so the idea, and it's the same thing. If you have a bathtub full of water, and did you see the thing with temperature with the 2 swimming pools, where he put the Eureka video?
Oh, not yet. I haven't. I watched the first. Yes, the 2 swimming pools. Yes, I did with the dollar bills.
Yeah, the dollar bills.
$150 bills.
Yeah, and so that's a wonderful example of what's going on. You have a bathtub, and you scoop a glass of water. They're both the same temperature. What's different about them? The amount of thermal energy. The bathtub has many more particles, a much higher thermal energy.
So that's really helpful in terms of the the thermal energy, the internal energy is all of them. It's it's 600 centimeters of height, whatever.
Yes.
Whereas the average is it's just an average. Yeah, that makes a lot of sense.
And see, this introduces the ideas, and with any luck, it changes their way of thinking about things, and the vast majority of them do.
Yeah.
Because it's stuff that affects your daily life.
Yeah.
All right. Temperature cannot be measured directly.
Yeah.
Properties that vary with temperature are used to measure temperature. For example, what's the property here? It's thermal expansion. It's how much this thing expands with temperature. I have another thermometer here. One of these.
Honeywell.
And what it is there is a spring that's wound around. It's a bimetallic strip. It's got steel on one side and brass on another. Allow me to demonstrate. Now I say this, I hope it's still in the same spot. Let's find out. Sweet. Bimetallic string. You've seen these before? Yeah. All right. So, but this will be important. Now, I've got steel on the inside and brass on the outside. Which one is expanding more?
The outside, the brass.
Yes. So for the same temperature, and usually I have a I've got a squirt gun with water in it, and it straightens back out. So that thermometer, the Honeywell, is a bimetallic strip that's wound in, and as the temperature changes, the needle goes up and down as those two things.
Cool. So what would you declare the property of that to be? Just a thermal expansion. Still, right? Okay.
What happened, because what's going on? You got these two metals, one is brass, one is steel, one is mainly iron, one is mainly copper. And as they bounce around, they will grow different amounts.
Yeah.
And we'll get into that here shortly. Okay, so here's our big three. Thermal energy is a total, depends on how much you've got, how fast the particles are going. Temperature is the average at speed only, and heat flows from high to low due to a difference in temperature. So this is the first big idea to get across. There's no such thing as cold. There is heat.
Cold is an opinion.
For example, I might as well tell you this story. I always tell students. My first year teaching, I was given a budget. And the first thing I bought was this globe. It's called a physiographic relief globe. It has bumps for the mountains and bumps for the mountains, and then here's the San Joaquin Valley. It's got a low spot for the valley. Okay, and I got this, and at that time, one of my best friends was a park ranger, and he was at Gates of the Arctic National Park in Bettles, Alaska. And Bettles, Alaska is on this globe. Bettles, Alaska has a population of about 60 people.
That's so funny.
Merced is not on this globe.
Dang.
Okay. And
so what is the significance of that?
Well, what's the significance of that is I got this thing in Bettles, Alaska, and in just talking to him, well, how cold does it get up there? And he says, well, it gets down to like 60 below 0 Fahrenheit. 60 degrees below 0 Fahrenheit. I say, wow. And so said, but people have to live and work in those environments. So what they have is they have the snorkel, like Kenny on South Park. You ever watch South Park?
I don't watch South Park. I'm like lame.
No, you don't. And so what happens is you've got this parka, and on the hood there's a long thing that has wolf fur around the outside. And what happens is you've got the 60 degrees below 0 outside, and then your skin heats up the air in between. And so because your eyeballs would freeze. Your eyeballs would freeze. So. But the interesting thing
so much for dressing cute.
In the spring, when things start to warm up to 30 below and 20 below, when it gets to 10 below, people are outside in t-shirts and jeans. At 10 below 0.
Wow.
And why is that? Well, it's not 60 below anymore.
Cold is an opinion.
And cold is an opinion.
Does that turn off? Aha.
We'll get to that, but see the shape.
Yep.
All right, so cold is an opinion, and you have a right to your opinion, but there's no such thing as cold. All right, thermal expansion and contraction is the result of changing energy of the constituent particles.
Cool.
Those are big words, Mr. Boyd.
Constituent particles.
Yeah, okay. Linear expansions in solids depends on the properties of a material and its change in temperature.
Now, before you use thermal expansion, what is linear?
Well, linear expansion is the simplest way of looking at it.
Okay.
Because linear expansion is expansion. So you have a thin rod, and it will grow and shrink as the temperature changes.
Oh, kind of like how the video was saying the spaces between on the road.
Yeah, come out here.
Ooh, Mr. Boykin. It's not as hot out here as it is in there. That is why.
You just want to wish you wore some pants.
Yeah.
Hi.
Hey,
Hello.
Ashley.
All right, so let's take a look at this. This is a rubber sealer. And notice the gap here. This is...
It's on this side, but there's a gap on that side.
Yeah, well, if you go back, there's a gap on both
Oh, I
sides.
see, I see.
If you come, and it's in the mid-50s out here.
Yeah.
If you come back here in the summertime when it's 105, that gap won't be there. That's because of the expansion. Now, it expands not only in just one direction.
Yeah.
It expands in 2 dimensions.
And that's what all of it's for, right?
It expands in 3 dimensions. Right.
Yeah.
Yeah. Well, not all of these. These lines here that are only go down about a ½ inch into the concrete
Yeah.
are to prevent cracking in the concrete.
Ah. Which is the result of the ground shifting plus the...
Well, it's a property of concrete.
Yeah.
It cracks.
Gosh dang
So
concrete.
you have how long your item is at the first times how much the temperature changes times a coefficient here. And it's a coefficient of thermal expansion. Page 373. Oh, here we go. Yeah, here's coefficients of thermal expansions for solids and liquids. And so we don't need to do any of these calculations, but you can see that it's a very simple equation. And if you want to find out how much it's going to change, and engineers have to do this when you're designing things, because things expand and contract with temperature.
Wait, so the L sub O is the length?
L is how long it is at a particular temperature.
Oh, okay.
So that's how long it is at a particular temperature. That's the original length, okay? And then you change the temperature, the length is going to change.
And that tells you the change in length, so you'd have to add this number to that number to get your...
Yeah,
if they
and
wanted
so-
to know the...
So, depending on what you got, brass or steel, let's see if they have brass and steel here.
Brass?
Brass is 19 times 10 to the negative 6. Steel is 12 times 10 to the negative 6. So this has a larger coefficient of thermal expansion. That means that brass side is expanding more than the steel.
Which is what we saw on the...
And, you know, it has here to do some problems. We don't have to do these problems.
It seems pretty straightforward. So the number one thing is there's no such thing as cold. The idea is that you've got the thermal energy, or the internal energy of the system, which is just all the energy of the whole. You've got heat, which is it goes from hot to cold.
No. High temperature to low temperature.
High temperature to low temperature.
So you have to train yourself?
Yeah, high to low temperature.
You're going to teach us.
And then temperature is temperature is the average. And is the average speed of all the molecules, whereas the...
Temperature is the average thermal energy of all the particles in an object. And because some particles in an object are going faster, some particles are going slower.
And in the video and in your presentation, you talked about how the thermal energy of the system, if that's the right way to say it, is the mass and the speed, and just taking into account that mass part, which I think we're going to probably get into for the...
That's the bathtub and the glass of water. They both have the same temperature, but there's more thermal energy, more internal energy in the bathtub because there's more particles. Let's see if we need to look at these circular hole. No, we're not going to do that. That's some problems involving thermal expansion. By the way, what'll happen here?
The metal, the heat will, the metal will expand.
Yep. So as I heat this up,
Because it's the particles, the molecules inside the metal are going to be going faster.
and this is brass,
More
so it has a
volume.
fairly high thermal expansion. And you have to get, I don't want to heat up the ring, because if I heat up the ring, it'll expand as well.
A little tricky there.
Yeah.
Put in some cold
Even
water.
cooler is,
So many fun things. So do you do all these things for the kids?
I used to.
Yeah.
We don't do thermal expansion in regular physics. That's
Oh.
that. Don't do thermal expansion in regular physics. Okay, that's that one.
Cool.